My name is Yuan. I'm the CEO and founder of OneClick.ai. So today we're going to talk about time series forecasting. Just out of my own curiosity, like how many people done AI before? Can you raise your hands? Oh, okay. Have you guys dealing with the time series data before? Okay. Oh, great. So okay. Today we're gonna cover three sections. So we're going to talk about first one is the very traditional time series model. People have been using this thing for past, 20 and or 30 years. Then we're going to talk about the traditional machine learning way to do time series. And lastly, and the most important is deep learning. So which is kind of buzzwords nowadays. How can you really leverage deep learning to build very decent time series model? So obviously we all understand why we're doing forecasting, because it's not a new concept. People are doing this thing for past few decades. They're doing different things about forecasting. We can do sales forecasting. You can do financial planning. You can do dynamic pricing. And right now, the amount of data we have just really coming from different places. For instance, for people browsing the website, obviously all those websites they log those user behaviors, so you can basically using those data sets to figure out people's future behaviors. And in the factories, a lot of machinery they install lots of sensor data, so that generate 24/7 data continuously. You can actually use the data stream to predict the health condition of the components, to figure out when you should repair them or replace them. And other things like people doing marketing, they're running a lot of campaigns. They get a lot of users clicks data sets. You can actually it's kind of streaming type of data sets too in certain angles. So you can actually use those things to really to understand your users' behavior, to figure out whether your campaign might be a success or not. In the health industry, people kind of continuously monitor patients, their heart rate, their blood pressures. So you can consider them as time series too. You can try to predict their future behaviors in X amount of time. So when we're doing the forecasting, there's a concept called granularity. Let's say me as a retailer, let's say we Nordstrom. So now they try to do sales forecasting. So really you can do on the sales forecasting on different levels. Let's say they want to get the total sales number for every store, for every product, or for combination of the product, or combination of the store or certain department. So really depends on the level of granularity you want to go to. Usually, the higher granularity level you go, usually you kind of the prediction power kind of lose because you don't have enough data to handle those kind of things. So when we're doing the forecasting, you can do short term, medium level, on the long term. For the short term forecasting, we all understand basically just for next few days or next few weeks. Restaurant, for instance, you go to Chick-fil-A. What if they can tell you what's how many burgers you need to make for next 1 hour? That'd be really awesome. And you can also use the short-term forecasting to kind of do the personnel scheduling for transportations. The medium level forecasting usually for for next few months. I think usually they use this kind of results to really instruct them to do the manufacturing. They try to optimize the amount of products you want to manufacture. They want to purchase raw materials. If they actually open in new locations, they want to hire the right person. All those kind of things, you should better understand the prediction numbers because it takes time to really get everything in place. The long term is more about strategic planning and a lot of factors that come in place. Not only you need to get historical behavior, but also you have to consider like economic factors, political factors, environment factors, those sort of things. So in a nutshell, like time series is actually quite simple. You can just think of it as a sequence of numbers. Given the sequence of numbers, you try to predict how the future looks like. So here, let's say we get numbers like x1 until xt minus 1. And obviously, this is very simple format. But now, because we actually sucking a lot of other data sets, right? For instance, Nordstrom, not only they have all previously transactions, they also know the store location, the population of the city that the store is located, even the foot traffic of the store, the temperature, or discount promotion, all those kind of information you can really leverage to help you to make better predictions. There are a couple of like patterns in time series. Here are those three are pretty common ones. The first one is a trend. By name, it's very easy to understand. Is this times this sequence going up, going down? Seasonality, very easy to understand too. Basically, for a lot of sales, obviously you see those patterns throughout the years. Obviously, you want to understand during this Thanksgiving or Christmas, the sales number will go up. Usually January will go down. The last one is called cyclic. It's kind of cyclic. You try to kind of to forecast certain repeating patterns, but those patterns they kind of vary a little bit. For instance, what if we try to forecast when the next time we'll have this financial crisis, right? This kind of tough. Sometimes you have a circle of 10 years or 15 years. Those kind of things kind of pretty hard to forecast, but still people they try to do those kind of things. When we all understand, like when you try to build a machine learning models, try to leverage the insight within data sets. When we build those models, we must have a way to tell whether this AI model is doing its job. So that's why we have this concept called like metrics. Metrics, certain way you can evaluate the performance of the models. For instance, let's say today I'm actually building models to predict how the stock, look like for the next few days. Usually my metrics can be the difference between the true value and my prediction value. Obviously, if your prediction is perfect, this value is kind of goes zero, but we'll all understand this is not realistic. So here are usually the pretty common metrics people they use. Like the first one, MSE, mean square error. MA is mean absolute errors. I mean, sometimes people really care about percentage. They just want to say, okay, I just want to make sure my predictions are within like 5% or 10%. I don't care about numerical difference. So you can use the MAP, which is the mean absolute percentage errors. But the tricky thing here is, if you guys can see my mouse here, is like, let's say if your true value is kind of close to zero, and this metric can go very large, which will dramatically kind of skew the whole distribution of them, the error metric. So usually people, they have another one, which is called semantic percentage edge. Usually the range is between like -2 and 2. So even if your true value is kind of getting to zero, you're not gonna get infinity amount of errors. The last one is like quantile losses. A lot of like factory or warehouse, they want to make sure 90% of the time they can actually meet users' demand. So you can use those kind of metrics too. So let's first look at the traditional time series models people have been using for past several decades. The first one, the simplest one, is called the simple average. So what we do is basically you just get all historical numbers and take an average. You use this average to as the prediction results. Here we have a nice diagram. So we actually fabricate this time sequence, and for past I don't know, it's like 12 years, something like that. As you can see, we see this like upward trend. Also, there are certain seasonalities too. One kind of the obviously thing I want to mention here is, like, as you can see, the variance or the amplitude of those variations kind of go bigger and bigger. So we try to see, using different models, can we really make better predictions? So here, so within this diagram, we have three colors. The blue is basically the training data sets. So when you use the AI models, you have to feed the data into those models, and we call them training data. And the green one is actually the test data sets. And once the model is built, we basically apply this model into this test set. We'll see how it performs. And the red one is actually the model's prediction result. As you can see, if you're using the simplest format, which is simple average, the prediction is kind of way off from the actual values, which is a green one. The second one is a moving average. Instead of, the difference between this one and the last one is the first one will basically just take an average across all the historical data sets. Here, I'm actually just, define a window, kind of moving window, and I'm actually taking the average values within this moving windows. As you can see, it's kind of getting a little bit better. It's kind of getting closer, but still, there's no way you can capture the trend and the seasonalities here, as you can see here. The red ones, okay. Probably you guys can't see my cursor here. The next one we call, the third one is exponential smoothing. So here, there's a little bit of mess here. I try to take it easy on this thing. So what we do here is basically, in previous cases, when we're taking the average, so which means we basically giving the same weight for all the historical numbers. But now people might have preference. They say maybe the most recent data, they should have more weights. So basically, we have alpha here as a weight. And you can apply different weight here. So within this diagram, we have the red alpha is like 0.2, the purple alpha is 0.6. So they actually generate a little bit different results, as you can see here. Okay, the fourth one is called Holt linear trend model. By its name, it's trying to capture the trend, up or down. So here, what they does is basically just add additional kind of variables called the BT, which basically try to capture the trend. And here is actually the result. As you can see here, it's no longer actually a flat line here. It's kind of capture the upward trend, which is great, but still you don't see seasonalities. The fifth one is actually, we take one step further, which is we try to capture this seasonality factor. This is actually still pretty easy. You actually add another parameters, which is ST here. And what does basically capture the seasonality, these factors. So as you can see, we kind of models get more and more complex. At the very beginning, we get a very flat models. Then later on, we try to add parameters to capture the seasonality, the trend. And this one, we try to capture the seasonality thing here. You can see it's actually doing pretty good. So I want to actually capture the whole, seasonality, also the variance too. So now we come up with what kind of most famous method in the traditional time series, which is ARIMA models, autoregressive integrated moving average. So this is basically the equation here. You don't have to understand, every term about this. So it's actually a linear model, as you can see. It's nothing fancy. So there are actually three parts here. Let me explain a little bit. The first one is called autoregressive. It basically says, today my prediction result is actually a linear combination of all the previous observations. And the second one is actually the moving average. The moving average is actually the latter part here. So it's actually still similar. It's actually a linear models here. And what it says, okay, not only actually, the current prediction depends on previous previous observations, but also it depends on the previous mistakes between what I predict and what actual value is. And the last one is actually the parameter D here, which is, we call it like these order difference sequences here. As you can see, when D is equal to 1, you have a little bit, variation in terms of equations. It's actually pretty famous, where you guys can do a little bit of research yourself. But one thing when you try to use this method on time series forecasting is you have to make sure your sequence is certain kind of stationary, and you don't have to understand all those mathematics. I'll just give the equation here. There's a Python library you can actually, very easy to use, actually dumping this time sequence, and it will tell you whether this sequence is actually stationary or not. If it's a stationary, great, you can apply it right away. If it's not, you probably need to do certain pre-processing on the time series before you can actually use the models directly. So what basically it says, in a very layman's word, it says, okay, if the sequence is actually stationary, let's say, if this is the wrong sequence, I'm actually defining a window here, and this window can random move along this sequence, and we want to make sure the joint distribution on all those points, they're actually the same. So basically, you have the same mean, the same variance. And because we understand here, let's go back to original, the diagram, the training data patterns. As you can see, it's actually, this sequence has a trend. It's actually upward trend. Also, it has this seasonality. If you apply the equation to to decide whether the sequence is actually stationary, obviously it's not. So we need to do a little bit pre-processing on the original sequence. So two things we need to kind of fix. The first one is the what we call it, this the trend. So as we can see here, let me go back here. As you can see, kind of the variance kind of keep, you start very small, then the fluctuation get bigger and bigger, right? So we try to make sure the same. So one thing we can do is actually apply a log on the original sequence data sets. So if you do this thing, as you can see, you kind of still keep the same shape, but the variance is actually kind of stable. Is the first one, the seasonality. The second one is the trend. We want to get rid of this upward trend. So what we can do is actually we can, instead of using original sequence, we can actually take a difference between two adjacent points. In this case, as you can see, if we apply the log, also take the difference between two consecutive points, you get a sequence like this on the left side, which is kind of like white noise, but they're kind of stable. If you take a different windows here, you can see they are like mean and variance are kind of constant. So in this case, you can actually apply the ARIMA model right away. The next one we talk about, because when you use ARIMA, very famous models here, there are three things you have to decide, which is we go back. Here is like the p-value. So we actually we have to look back, past p points. Like what is the right p? Is p is equal to 1 or 100? This is something we need to decide. It's really sequence dependent. The second one is the Q, the same thing. How many steps we need to go back look at? And the last one is D. So there's another interesting tool. So you can actually plug and play, and they will tell you, okay, they'll actually draw this diagram. So they'll tell you, what is the right value for P and Q. So those are basically the way when you try to use ARIMA models to do a forecasting. And here, ARIMA obviously is kind of a generic group. There's people doing a lot of other variations. So seasonality ARIMAs. So the point is just getting the model to really capture all those little things within the sequence. So those are actually the kind of a quick summary of those traditional time sequence people are using for past couple of decades. So there are kind of pros and cons. The pros, obviously, the model is a linear model. It's very easy to understand. If your production is off, it's very easy to go back to do the math to figure out which part is actually, making the mistakes. Are you maybe it's a mistake, or maybe a lack of certain factors. And you only need historical data sets, which is pretty easy and very easy to understand. But the con side, the drawback here is, what if I have other information? Let's say we talk about, what if I have this promotion informations? What if I have temperature, foot traffic, those kind of informations? It's possible you can, as long as there are numerical values, you can still can go back to the drawing board, to go back to very original equation we talk about here, to add those factors. But it's not kind of easy job to do. But what if our promotion is actually like text, like 20% or 30% or something else, right? Then you have a challenge here. And also, when you use a ARIMA model, it's very hard to really capture the correlation between different time sequences. Let's say the Nordstrom, right? They're actually selling thousands of different clothing SKUs, we call SKUs. But actually, some of the sales of SKUs actually contradict with each other. Let's say maybe in the summers, they're more likely to sell, the shorts versus big jackets. There's a certain kind of correlation between different SKUs. And if you use ARIMA, it's very hard to capture those correlation across different time sequences. And now what if you have like 1 million SKUs? Which basically you have to, build each ARIMA model for each single of them, which is like 1 million. So it's a lot of work to do. So it's not, a good way to scale. And also, if your sequence really kind of long, maybe more than like few thousand points, then the result will be kind of tricky. That's why next one people really say, can we just take one step further? Really leverage machine learning to do a better predictions. The answer is yes, we can do a little bit better. So what is actually essentially is machine learning? Machine learning is actually a function here, and input is basically X, and output is Y. So what we try to do is to figure out what is exactly is this F function is. And we have the training data sets, which is X, and we try to predict the final result, which is Y. And there are a lot of machine learning models nowadays. Common ones like linear models, linear regression, generalized linear models, all the fancy one like SVM, boosting trees, random forest. And each one have a little bit different characteristics. So when we're using our machine learning methods, so there's certain general practice we need to follow. I think the first one is actually the holdout. So one of the mistakes people will say, okay, my model is actually overfitting. Why is that? Because they usually don't use the validation data set, or they don't use the test data set. The first one is once you have this whole data set, usually what they do is actually they divide them into 3 pieces. The first one is actually training, and the second one is validation. The last one is test. So during the training the training procedures, so you have 2 arrows. One is the training arrow, the other one is validation arrows. So you can't always see the training arrows because training arrows are always going to go down. So at the same time, you have to see how the validation arrow is going to go. If the training arrow goes down but validation arrow goes up, that means you kind of overfitting. So you have to do something about it. You probably need to stop right away. The second one is actually you can use the cross validations. So let's say you have 3 folds. So what you do is basically you chunk the data sets into 3. Here's actually K folds. Let's say you chunk data into K pieces, and every time you use K minus 1 pieces to the training and 1 piece to the validations. You kind of iterate through like K rounds. And for time series, there's other variations you can do here, as we can see here. The purple one is training, the yellow one is validation, and the orange one is training, the yellow one is the validation, purple one is the test data sets. So as you can see on the first fold, I kind of chunk them into like K pieces here, and kind of move away. Like first round, you have a pretty short training data sets and short validation sets, but pretty long test data sets. As you go to further down on the number of folds, kind of training data gets larger and larger. So this actually works pretty well if you don't have enough data sets, because you want to make use of them as much as possible. The other variations here is, okay, what if I want to have a fixed size of training data set? You can still do this. You basically just keep moving on the right directions. And once you come moving along, you kind of drop all the data sets on the left. There's another way you can do. So which way you want to pick really depends on your business need and amount of data sets you want to use. Okay, so those are actually we talk about when you build models, we need to really kind of care about how you slice and dice data sets to build models. So here, when we build the models, right, 2 ways you can actually build machine learning models to the forecasting. The one is we call 1 step ahead. So basically what that means is we understand you have to feed in a lot of inputs to the models and generate outputs. Here, the inputs are actually historical data sets, like y t minus 1, y t minus 2, y t minus k. So those are actually the inputs you feed into models. And output is just the count time, which is yt. So we only make predictions for 1 time step. And as we can see, it's kind of a iterative mode, because once, let's say, those are actually the data point until yesterday, and now we try to predict today. Then once the the prediction result for today is available. You feed back and try to predict the prediction result for tomorrow. It's kind of an iterative way. The second one is, what if, there's actually pros and cons here too. And, the drawback is obviously because it's an iterative way. You kind of use today's prediction output as tomorrow's model's input. So if you make a mistake, this kind of mistake is going to accumulate throughout the way. It kind of getting worse and worse. And, the model, there's no way you can actually really capture the long-term effects. There's a different ways, actually. What if I just, I actually predict, several steps at the same time instead of just one step. As you can see, it's the same thing. You're feeding the same input, y(t-1), y(t-2), until y(t-k). What I try to predict, not just tomorrow. I try to predict, a couple of days. Tomorrow, the day after tomorrow, a couple of days. So you can do so as well. So the good thing is because we don't kind of rely on previous method, you kind of get the output, then you feed them back as input. Here, just you do it once. So which means the chance to get accumulation error goes down dramatically. The second one is you kind of learn those dependency across different data points. Any questions so far? Yeah, keep going. Right.
So you're assuming that you don't shuffle the data set.
Usually time series you don't shuffle the data sets because usually it's a bit different for classifications. There's not any time dependence, but time series I usually don't recommend people do. Yeah. Because think about it's always a sequence, right? There's always certain time dependence, right? Like for past 3 days, 30 days. You don't want to just mix this year's data sets with like last year's. Like it's not gonna work well. Yes.
So what happens is if there's any empty days, number of days, in one of those data sets, how do you fill up the data?
You mean the missing data sets?
Yeah, let's say if you're 1, 2, 3, 4, and you're missing it for 3 days, consecutive, what's the value of that?
Right. I guess in this case, it's definitely here, right? It's the same thing as we do other kind of missing data sets. Is a default value make sense to you, right? Really, it's kind of you have to really application dependent. Can you use the default values? If not, can I? What if I remove them? Is it gonna be detriment to the models? So you have to make those kind of judgments. So. There's actually some chairs in the front if you guys want to come and sit. We have a couple of chairs here. And some pizza cells around the back. So, okay. So, we know we can build machine learning models. One is to predict just one future data points. The other one is we predict a couple of future points at the same time. Obviously, when we use machine learning, you have to do a lot of feature engineering. People complain it always takes a lot of time. That's true because when we dealing with time series, you really try to come up with the right features to capture all those historical trend, seasonality, lack features. So it's a lot of work to do. For instance, I'll have examples later on, and that's something you definitely need to spend time to work with because without decent feature engineering, usually the model just sucks. And the model is a lot of choices you can choose nowadays. I will talk about general linear models. Usually it works pretty well, to my surprise. And other ones, pretty popular ones like boosting trees, random forest is kind of pretty common ones. If you go to like Kaggle time series competitions, people use a lot. And you can use like SVM Gaussian process as well. And here is actually kind of examples we kind of follow from Kaggle, I think, is we try to predict the sales numbers for each grocery stores. Here they have 3 different tables. The first one is the date, store number, and sales number. The real one is actually what we try to predict. And also you have other features regarding with your store. Let's say the location of the stores, the state, the type of stores. And even for the items, the product they sell, they have other attributes. So when you get this data set, those 3 different tables, you try to figure out, okay, what is the right way to do those feature engineerings. So there's no either way. You just have to really understand data sets, just come up with the right ways to do those features. And here, so training data sets is actually 4 years, more than 4.5 years, since like 2013 until 2017. And this is actually the data points, as you can see in the diagram later on. And what they try to predict is just 2 weeks. As you can see, a lot of variance within data sets, and even like certain outliers here. So what they have like 54 stores for some items, and the combination of the store and item is actually 174,000. So think about, if we go to very traditional ARIMA models, so you have to build 174,000 models for you. And here using machine learning is just, it's much quicker. You can basically use one model to do everything at the same time. But you have to spend a lot of time to do feature engineering, clean up the data sets, make sure, the data, the input and output actually makes sense, align with each other. As you can see, what happens here, these outliers around like January of 2015 is actually the earthquake. So, a lot of people, when we do those feature engineering, they kind of, ignore those environmental factors. So it's kind of important. And some of common features, like in this examples, you can really do a lot of statistic type of features. For instance, for this kind of stores, you can get historical past 7 days of average sales numbers, past 30 days average sales numbers, on different store type, item types. Just a lot of feature engineering can do. Lag features is like past 7 days makes more sense versus like past 14 or 21 days. You just have to do a lot of try and error to see how it goes. And also you have different like categorical features we talk about here. Let's say if you have the city name, if those are actually non-numerical data sets, right? If you're using traditional ARIMA, there's no way you can actually use those informations. And here, machine learning, they can handle pretty well, especially like in decision trees. And other things like you can kind of manually come up with the day of the week, promotion, months. And people use a lot, like Microsoft, like GBM or XGBoost. They're pretty decent tools you can do this. Okay, so we kind of give a summary of the traditional machine learning methods. What the good side is they can really handle very large amount of data sets. And usually the model is pretty easy to explain because it really depends on different industry. And especially like financial, insurance, or health, once you build a model, they're always asking you why the model is actually making such prediction. You have to go back as a data scientist to explain, okay, because X and Y. The drawback is obviously we need to spend a lot of time to do feature engineering, and sometimes generalization of the model is not that great. And correlation between different time series. Let's say I'm actually, the time series for SKU1 versus SKU2. Sometimes you can capture the correlation. Really depends on how you do those feature engineering. Sometimes you don't. So those are actually the drawbacks. So the last one is, I think, the most exciting is the deep learning thing. So deep learning is not actually a new concept. People come up with this neural net concept back in like 7 days or even 6 days. The reason why the neural network never take a left is because 2 reasons. The first one is at that time we just don't have enough data sets. The second one is just computers was not that powerful. But now all those 2 problems has been solved. That's why deep learning actually make a huge impact in the industry. So we're talking about deep learning. Deep learning we try to build certain neural networks, try to simulate the way how our brain works. Our brain has billions of neurons, and we're not sure even we're not sure how those neurons actually they work together, how they connect each other. So right now this format is just like the simplest format that we can think of. You have basically the inputs on the left side. We have 3 inputs, and the output is actually on the right side. So this is the neural networks, and they actually connect with each other. And why people say, why use deep learning? Obviously, as you can see, this neural neural network can go very complex. Here it's just like 4 layers. You can think, or you can build all kinds of different shapes, different neurons. They can actually talk to each other. So theoretically, you can learn any functions as you want. And a couple of examples. Previously, like Microsoft, right? They're working on the speech recognition system. It's a lot of works. Big teams working on this, projects, and every year they kind of tweaking the system, come up with new features, but still the accuracy is almost like flat. So once they kind of using deep learning, it's like a big jump right away. And deep learning, the second point is like no feature engineering. Sometimes you don't have to do feature engineering. Why is that? Because, for instance, like give an example like image. Previously, let's say I was actually, my first AI project was actually teaching the computer to recognize the tumors within the CTs. So when you build the AI models, you have to really come up with the right features. Let's say you have to understand how big the tumor is, usually with the shape, the color, the density. So without those domain knowledge, there's no way you can actually, build models. But now using deep learning, because you can make the model very complex, and when the model, the complexity of the models actually really you take away of a lot of efforts to to really build those decent features. So in a lot of ways, even nowadays, you don't have those kind of domain knowledge. Still, you can go to Kaggle just doing competitions to try to figure out the tumors, how to detect those tumors. That's a good thing. And the third one is actually you can really handle unstructured data. So we talk about image, we talk about text, we talk about the videos. Okay, all right. So here, so go back to the time series. So we actually, there's actually a couple of ways you can build the models with the deep learning technology. The first one is we're actually building very easy 3-layer neural networks. This is actually still one step ahead. We use historical data sets, just try to predict tomorrow the numbers. So here, the input is actually very similar to machine learning ones. You have the input xt, xt minus 2, xt minus until k. And the output is actually basically tomorrow, yt. So once you get tomorrow's prediction results, you feed back as the input for the day after tomorrow. So you kind of doing this iteratively. The second one is, okay, what if I just, I want to get the prediction for the next few days? You can do the same thing. You can build similar neural networks. It's very easy to use TensorFlow or Caffeine to write models in this ways. They usually work pretty well. So what if we just take one step, even further, which is we call recurrent neural networks. So it's a little bit different structures as the first one. So why people using this one? I think obviously the first one is, as you can see, usually the input side is actually the fixed. But when we dealing with like text data sets, right? You want to or chatbot or some random length of inputs. Usually the first neural network is the vanilla neural network is not the best choice. It's here people come up with recurrent neural networks, and basically you can feed in the data points like this way, and this can have variance length. And on the upper side, it's actually the output you try to predict. It can be a time series. And usually people try this neural network. It works pretty well on the NLP problem, like speech recognition or machine translation. It's actually very easy if you know how to use like Keras or those libraries. They already have this functions to do to support like LSTM or Giant. So it's very easy to use. And here is actually a very interesting case study, which is Uber they use. So what they try to do is actually they try to figure out the number of trips within a day across different time of the years for this given city. As you can see, kind of during the new year, the number of trips of the Uber just goes down. So what they built is kind of like a hybrid of recurrent neural networks. And here on the left side, they have the encoder models and the decoder models here. And what interestingly is they're actually doing something a bit different. Usually when you build models, you just need the models like the green boxes here. Right? You have you feed those inputs, you try to compose those outputs. And the LCM should work quite well. But what they do is a bit differently. So once they build these models, they kind of completely get rid of the models on the right side. And they actually just need the vectors here. And feeding these vectors into another neural networks to the predictions. So it's kind of a hybrid of LSTM with the traditional vanilla neural networks. And it just works pretty well on their data sets. I'm not sure if this is go-to way to do. Yeah, I think it's something you should try. And every data set will have different results. And the next one is the convolution neural network. It's another format within deep learning, and people use a lot in the images. So what basically it does is here, let's say on the left side is you have like image data sets, and they basically apply different kind of mathematical equations on certain portion of the images, and they generate a bunch of other interesting images. They find certain ways to combine them together. That's basically how it works. So one example is, let's say this is the very original image, and the image is actually a lot of pixels, and each pixel has a value here, and they can apply certain features here and do certain numerical calculations to get one values here. In this way, your image can get smaller. And you can do a lot of different kind of size of features with different values. So in this way, you can create a lot of other, feature maps, what we call here. Then you can find certain ways to combine them together to do downsampling and use those, intermediate results to do the prediction of the models. And there are actually a couple of things I want to mention here when we're dealing with the new convolutional networks. So let's go very basic thing, which is the building blocks. If you're using Keras or TensorFlow, they have like different layers, like convolution layers, pooling layers, fully connect layers. And obviously, you can have certain ways, you can organize certain ways as you want, but there's also always certain like routines, way people they do. Sometimes it works, sometimes it don't work. And also, they have local connections and the different padding size. So I'll have a little bit explanation later on. So actually, very basic elements when you're doing the convolutional networks. So one very simplest form is actually, given a time sequence or what I understand. It's not like an image. Image, you have two dimensions, right? X and Y. But for the time sequence, I just have a sequence of data points. You can actually do one convolutions. It's very similar, is it? Okay. Here within this example, is okay. For every 2 JSON points, you kind of apply certain mathematical formulas to get another points, and etc. So, and the next one we call the casual convolutions, because we all understand when you try to use historical data points, you always try to rely as much as you can. Let's say, especially, this sequence have, the long-term effect. And today I'm actually making prediction of today's numbers. Obviously, I try to leverage as much as, past X amount of days. So here, that's why they come up with like casual convolution. As you can see here, this point right here, I point here. And actually, let's see, okay, okay, you can see here. Okay, here is actually the inputs. You have xt minus 7, t minus 6 into xt minus 1. And here is on the upper side is actually basically the output layers. It's big. And here might be xt minus 6, xt minus 5 into xt. So let's say if I try to predict these data points, given this diagram, if you trace back all the way, let's say this is the data points I want to try to predict, and you trace back, you can see, okay, it basically just rely on 3 days of inputs, because that's how the neural network architecture constraint, because that's how it looks, like in here, because you need this points go this way, and this points go this way, and this point go this way. So which means today I'm actually predicting these points, I actually only leverage past 3 days of data sets. But you will say, okay, what if I want to use past 4, 5, or even 20 days. In this case, you just keep adding new layers. Like this, like 3 layers. So you just keep more and more layers, and just kind of really gradually go to cover all historic data points. But obviously, downside is as you're adding more layers here, you need more data sets, and the model get very complex because a lot of times you want to serve the traffic live, right? So okay, I'm building time series models, and I want to predict tomorrow's stock price on a second basis. Obviously, when the model get very complex, you have a big latency. So that's kind of something people don't like. So they actually come up with another format, which is called Dilute Convolutions. What if I still want to capture all those historical exponential days of data points, but I just don't want to build very complex models. There's certain ways you can do this. So instead of each point they actually connect with each other. We can build models just like randomly it connects several data points. So in this case, it's here in the let's say if you draw the networks, you design the new networks in this ways. Let's say today I want to predict this data points. I don't know, my cursor is just go. And here I can go this way and this way and this way. So basically just actually leveraging past the 8 days of data sets instead of like 3 in the first cases. And you can design any way you want. You can point to here, you can point to there. So you can try different variations. And here's actually good examples. Here's actually the DeepMind, which is the company who designed AlphaGo. So they actually built a model to try to simulate the way how human talks. So it's actually it was talked by machine, but it's almost distinguishable from human talking. So it's basically how it works. You have new points. It kind of do the predictions, and this prediction results goes back as the input. You just keep iterating in this way.
So the hidden layer, is it the fully connected dense layer, or is it one D convolution?
Here, right, it's not fully connected. It's neural, yeah. So it's just really you can do. I mean, you can try different. It's just the way you construct this neural network. You have a lot of possibilities. So this is just the way they design their neural networks, which is diluted one. So as you can see, all those points, they're not just talking with each other, just pick several points and they just skip 3 points here, 2 points there. So that's basically how it works. And someone said, what if I combine convolution with LSTM? Because usually the convolution neural network, they can actually really capture the spatial information within data sets, and the LSTM actually can capture the temporal, the time correlations. And here is actually an example is you can given this is a map, you try to figure out, okay, for certain routes you try to figure out the traffic volume. So there are 2 dimensions of information here. The one is the map. It's 2D map. It's a picture in this way. And the other dimension is actually time, because all you understand, like the traffic on weekends are obviously different from the traffic on weekday, even on the same route. So, but what they do is basically kind of combine those things together, apply CN on the map, and on the time dimension that you can use LSTM. You can really combine those 2 things to capture both the spatial and the temporal correlations. It works pretty well. So you can see it's actually trying to predict the traffic volumes. So here is actually I give a quick summary about when you should use different ways to build the time series models. Let's take a careful look here. Let's say if I only have a very single sequence or few time sequences. In this case, you don't have to go to use very fancy one like deep learning or machine learning. You can use very basic traditional time series model like ARIMAs. because it's very easy to understand, and you're only dealing with few time sequence. And because if you're using this one, use deep learning, because deep learning, I need to really suck in a lot of data sets. You only have like few time sequence. It's not going to do anything good. And most likely your model is not learning something. Just try to memorize all those data patterns. And next one, what if I have a long time sequence and kind of a lot of time sequence like Nordstrom, and they're selling thousands of SKUs. That's that problem trying to solve. In this case, and you can kind of use all those trees. And if SKU is kind of within a few hundreds, using traditional still makes sense, and you can easily go back and debug them. And if you're using traditional machine learning, it's still doable, but you need to do a lot of feature engineering. In the deep learning, I think it's probably it's kind of best, because not only you can learn all those like long-term effect, you want to see those things. Also, you don't have to do a lot of feature engineering in that regards. And also, when you build those models, the deep learning models, you are just not building models for each single time sequence. When you build a model, you just consider all those time sequences together. So it's very easy for the model to be able to learn all those correlations about those, especially for those like competing SKUs. You're very easy to understand. Okay, if this SKU sales goes up, the other ones goes down. They can capture those little trivial things. And if we take one step further, not only you have long time, a lot of time series data set, you also have a lot of other features, like we talked about the traffic, the foot traffic of stores, the promotion, the discount. In this case, you have a set of not only those numerical transaction data sets, you have another set of features. In this case, I think it definitely should go with the deep learning, because for using the traditional time series like ARIMA, it's almost impossible to dealing with those categorical or text data sets. And in the traditional machine learning, you can still do it, but a lot of feature engineering, it's not quite easy to do. And especially using even XGBoost, you can easily dealing with those categorical data sets, but if it's the logical regression, so you have to do a lot of feature transformations. And in the deep learning is kind of the way you should go. So I think the takeaway here is we talk about the traditional time series models, the machine learning ones, and deep learning ones. Obviously now the whole industry and all academia is actually moving to leverage the power of deep learning. The most challenging things on the deep learning is actually we're dealing with neural network architecture. And the way you build those architecture there's millions of combinations. There's literally no way you can try each single of them. And each time you try something, it takes, I don't know, depending on the data sets, few hours. And it's very costly, because dealing with deep learning, you most likely going to run the models on top of the GPUs, and GPU is not cheap. If you're using Amazon, usually I think the cheapest ones, probably like 90 cents every hour. So that's why I still feel like deep learning is kind of, it's the way to go, but still it's not easy for people to handle, because they don't have the right knowledge to know how to build those architectures. So that's basically what we do here is not only so here is have you guys heard Google AutoML? So what they do is, okay, today you have this image classification problems. What they try to do is, given this data sets, what is the best neural network architecture that you can find? So what they do is basically, it's more like a try and error method. So they kind of given original data sets, they try something, and if it works, and they have this results, they feed back to the original model and try to kind of iterate, from there. They use technological reinforcement learning. You can do it this way, but usually it's kind of costly, and usually for them, you have to go through about 10,000 rounds to be able to find pretty decent models for them. And also, usually, that problem, let's say today I'm actually giving you an image classification problem. Tomorrow, I give you another chatbot data sets, and they have to basically try everything from scratch. So those knowledge you can't actually borrow from one data set, to the other. But theoretically, you can do this kind of thing, especially dealing with image data sets. Right? Not only today, I'm dealing with the image data sets about dog versus cat, or I'm dealing with image data about satellites. Right? All those things kind of similar. All those knowledge is that kind of similar. So what we try to do here is not only we can build those models given data sets. What if we kind of accumulate all those knowledge across different data sets, right? You think about it as a data scientist, you dealing with a lot of data problems, and today you try X and Y, and some work, some don't work. You try to extract those knowledge, and tomorrow you see a similar problem. You kind of say, okay, this is the way to go. It's kind of similar ideas, and given data sets, we try to come up with right architectures. Sometimes it works, sometimes it doesn't work. If it doesn't work, that's okay. We try to think back this, the loss function, go to the controller and to keep trying new models here. And so what we do here is you guys can try our product. So it's kind of a link. You can try. It's very easy to use. This tool doesn't require any data science project background. So you can easily dump in a time series data set and see how result works. And I actually have a quick demo here where you guys can take a look how you can use the platform to do the sales forecasting. Let me switch my gear a little bit. Let me exit to my here more. And the show here, let's see here. Okay, let's switch gear. You guys see this diagram? Okay. Views, feed to screen. It was actually the UI. You guys can try this product. It's kind of free. We give free tokens. And this is kind of the product we're actually developing. So you have the project on the right side, the list of projects. In the middle is actually a chatbot. So instead of you trying to figure out different menus, how it works, you can basically ask chatbot what kind of things you try to do. And here I actually create a projects here. Let's see, do demo here. We can actually try one time series here, which is here. Let's see. So this is basically a time series data sets. Let's upload this data sets. And as you can see, let me take a pause here. Basically has like 4 columns. You have the store ID, you have the department ID, you have the date, and the weekly sales number. That's all you need. So everyone who can prepare, you can prepare such kind of data sets here. And once you upload data sets, you have to choose what you like to predict, which is the weekly sales numbers. And we know this is forecasting instead of classification versus regressions. And the metrics here, we talked about earlier. So you have to design this thing ahead of time, given your business problem. Here, the data column. It's very easy to understand data column. The next one is the reporting column. So we talked about you can go to different granularity level. You can get a sales number per every store, or per every store and every department, or even every SKUs. So you can choose different combination of them. So the next one is actually forecasting range. You can say, I want to get the sales number for next 1 week, 2 weeks, or 4 weeks. And here, you choose 2 weeks. And the next one is actually the running duration. So really depends on application. For instance, like Burger King, right? They try to do this forecasting for every an hour. They will try to figure out, how many burgers they need to prepare. In this case, they're gonna keep running this thing like on a routine basis. So you can decide, okay, which day, starting day you want to choose, and ending day. And within those time range, how often you want to run those models. And then update sequence is 2 weeks. Basically, so okay, every 2 weeks I'm actually running the model. So then you basically type, submit the models, and you just keep running. A lot of models we build here just all depends on like deep learning. So usually deep learning works the best models here. So after the models complete, so basically it will provide the prediction results you can download. Yeah. Here's the result. You can take a look. Yeah. So yes.
Can you actually get prediction intervals? You know what I mean by prediction intervals?
Not really.
Okay, so a lot of time in industry,
Yeah.
the prediction is just an estimate,
Right.
and you want to have some level of confidence as to
Oh
that
yes,
estimate.
yes, right, yeah. So we're actually working on these features because using like traditional ARIMA, it's very easy to come up with a confidence bound. But deep learning is a little bit tricky, so we're still working on this thing. We'll have a feature in a couple of weeks. So yes. And here I also want to show one thing. Here's like this is actually model report. So once actually given data sets, we're gonna build a lot of models, and some of models actually maybe the traditional machine learning models, some may be deep learning. So really depend on data sets. And each model, you'll have different scores here. This is actually classification report page. It's not the forecasting, but just give you a sense of how the list of models we build here. So here you have different metrics, and each metrics will give you more different metrics you can track and different latencies. So usually when we provide users the prediction result, usually we pick the best one with the best metrics. But obviously, you can use API to choose any models you want. So I think that was about it. Any questions so far? You guys should go there, and I have a link here. I can try and sign up very easily. So
Deep learning, typically, how many data points would you say is good enough?
That really depends. That really depends on time series. Usually, I think a few hundred, few thousand, like few hundreds, like at least you need to have. Is that right, Santa? Yeah.
So we say like for some they said that you only need like 2 or 3 years data, but for other industry maybe you need like 10 years and then maybe millions of rows data.
Yeah. Different applications. Sometimes if your pattern is kind of obvious, it's kind of not hard to capture. You need to you just have less data sets. If it's you have a lot of fluctuations or of seasonality. Usually, you want to go a couple of years back in order to capture those things. Yeah. Yes.
So let's say I tried it, I like it, and how do I integrate it into my business?
Two things. That's what we see. For the first one is if you're doing time series data sets, you can upload data sets into the platform, and the platform can make a prediction, tell you the results. For instance, where you just show, you can have a results to download. You can use this, result to manually type into your system, whatever way. This is one way you can do. The second one is you can actually, we have API. You can actually, do you know what API is? You can hook up to the API. So you can have the live stream data sets, and you can generate predictions. You can use the two ways.
So with the API, like if my training set is very big,
Yeah.
how do I do?
You can upload. You can still upload. So a certain size, but theoretically, as long as you have very beefy machines, you can upload. Still kind of big. Or if we see people, they want to run this thing periodically, programmably. They don't want to like manually upload. So we have the SDK. You can actually integrate with the SDK. You can write a program. You say, okay, I have this kind of data sets I want to upload, and then I want to predict certain columns using forecasting models. You can do it this way, writing program. So yes.
What about, have you thought about database connector?
Yeah, we have supporting a lot of database. It's more on the demand, on demand basis. But because our targets like business users, I'm sorry about that. Business users usually they, as long as they can handle the data within Excel, it should be good to go. So that's yeah.
Sorry if I missed it from your demo, but the model that you return to the user, is that a black box, or can you
know, like, oh, this is an arena and these are the parameters?
Right now it's black box. We try to kind of provide two levels of transparency, which is actually we are working on. The first one, especially getting deep learning, it's very, we can give you the whole architecture, but even if I given this very complex neural architecture, it's very hard for me to kind of really to debug if something's broken, right? Think about like self-driving car. If you hit a person, they have to go through all those layers, no binary, to figure out what's going on. So we try to kind of tell you how, in general, how kind of different components we put together. This is one thing. The second level is on individual data points. Let's say today, given this data points, we make such prediction. We'll tell you why, because you have feature X value, something like that. So, yes.
Could you talk a little more about the
Ultima part?
Do you do just a grid search?
No, you can't do a grid search on it's. On traditional machine learning, people are using like Bayesian optimizations to quickly kind of do a parameter sweeping, something like that, or even do like random search. You can work out because the model is very easy, and you can get feedback right away. Think about if you're dealing with like image net, it's like huge, and each iteration just takes forever, and because you're dealing with like a random forest, you only have X model, maybe like 10 parameters you want to play around. But deep learning, so many millions of combinations, like how many layers, the side of layers, hidden layers, different activation functions for each individual layer, just like so many possible ways. There's no way you can use. So if you have very powerful machines like quantum computing machines, probably it's doable, but it's not the case now. So that's why coupled with like Google is doing like reinforcement learning type of things, and obviously we're using it different ways. Still, obviously, you can't try everything. You try to build a model to simulate the whole process, right? You try something, you come up with a result, and you feedback this information to the models and let the model to kind of keep going that direction. So. Yeah, it's always kind of challenging. Nowadays, we look at literature like neural network architecture become hot topics. Everyone's using different ways. In some work, some people even use like evolution, like genetic type of algorithms to kind of. But still, like it's very hard to, come up with like optimal solutions. Always like sometimes you are stuck into local points, so optimal points. So. So we'll have a different section on automation, how it works. So yeah, so we'll have different sessions too. Pretty interesting. Yeah.
Do you have any limitations on how many cycles you can go through that loop so you avoid overfitting on your validation data?
It really depends on data sets. If if I don't have too much data points, probably you try to take it easy, and you don't even want to go use the deep learning things. If you're using deep learning, so like Google cases image, nets, they try like 1,000, 10,000 like iterations, and but the way why they try this is because they kind of start from scratch. They assume zero knowledge about the data sets you start with. So there's like search space a lot, right? What if you kind of understand it's kind of those are image data sets, certain characteristics within data sets. You kind of bootstrap a little bit better. So in this case, your iteration can go down dramatically. And what if you're just building models for like hundreds of image data sets? You have a much better idea how you should start with and how the network should start with. You kind of dramatically reduce your search space. So. Yes.
What are you using on the background for your website? Are you using some web services?
Yeah, some like Apache web services.
So it's in-house hosted. It's not a cloud service.
It's a cloud service. It's actually sitting on AWS. Yes. Yeah.
So you charge your client.
Yeah, like more like pay as you go. So you consume certain like AWS, right? You consume 1 hour of computing hours. So we charge 1 hour. Yes.
So yeah, it's clear that you don't do research for still. What does the general analytic process like you just array over a number of layers?
Yeah, you can think of the like building blocks, like you can just go back to the very basic of neural networks. You have different layers, you have different activation functions. You kind of just like building everything like a Lego, like layer by layer. So not only we build the neural network, sometimes we build the neural networks together with certain feature engineering, feature processing together. Let's say for this data sets, right? I want to do certain normalizations or certain, I want to apply a law. You want to put all those things together. Yeah.
Do you actually experiment with transfer learning?
Yeah, we use a lot of concept of transformations. Yes, a lot of people use transfer learning, especially on the image. It works pretty well, but you can use like pre-trained. Yeah. Yeah, like for us, it's like, when we building, like, for instance, like NLP models, right? Every text is different. English or Japanese or Chinese is different. But essentially, what we try to do is like to convert those kind of data sets into certain vector, certain space. And a lot of times those vectors are actually similar in certain ways. You can actually leverage transfer learning too. Yeah, but usually, transfer learning doesn't work that well on the NLP problem. Image problem is much better. So, yeah. So, and sometimes, especially, let's say you build a recommendation system, right? Not only you have images, you have text data sets because you want to have people review and description items. They kind of have, two things together. That can get very complex. So, yeah. Cool, great. Any other questions? Yeah, I encourage you guys, even if you're doing your own research or data science, you can use other libraries too, and to feel like, because I feel like time series is going to be big. Now there are a lot of attentions put into there because a lot of data sets, IoT generate a lot of sequence data sets, and even like for instance, like traditional in the bank they do fraud detection, right? If you look at like American Express or Visa, they have a team of like 100 people doing fraud detection because it's a big deal for them. Doing a lot of feature engineering, lots of features, like thousands of features. Essentially, if you consider as a time series, the problem will just get much, much easier. So, like customer churn rate, the same thing. So, as long as you can form the problem as a sequence data sets, you can use a lot of interesting deep learning technology to automatically figure out certain correlation across different historical data points to capture those correlations. So, instead of just manually to try different features, that's take a lot of times. Yeah. Great. All right. Thanks, everyone. Yeah.